Thank you very much, Per, for the introduction. Good afternoon, everybody, and thank you very much for the invitation to Copenhagen and the possibility to talk about the building materials stock. I would like to start to demonstrate the relevance of this anthropogenic stock as a reservoir for future resource extraction. And then I would like to continue with approaches how to determine the anthropogenic stock. And then I would continue, this is the main focus of my talk today, about the case study of the city of Vienna, how we try to determine the materials that are stocked or stored in the city of Vienna. And I will end my talk with a summary and conclusions. What is well known is our society, our well-developed societies, we have a growing consumption of resources. Here you see world production data over the past century, and you can see for some materials we have let's say some kind of linear growth rates. We have even exponential growth rates. We have some materials maybe where the consumption stays more or less constant, for example for lead, probably because many uses of lead have been phased out in the past because it was realized that lead is a hazardous substance, so like lead in gasoline or lead for plumbing or so on, we no longer use. But generally we have to see, we worldwide we have a growing consumption of resources. And the Bundesanstalt für Geowissenschaften und Rohstoffe in Germany, they once compiled how much materials are consumed over an average lifetime of a German person, but I think we can well translate this also to a Western Europe person, and altogether we consume around 1,000 tons of solid materials. Maybe lignite here, brown coal is more a German specialty, but what you can see is that many of these materials are construction materials. So sand and gravel is mainly used for construction purposes, also hard rock, limestone, also steel. Most of the steel goes into construction. So many of the materials that we consume are used for constructing buildings or infrastructure. And once we had the opportunity to make a rough materials balance for the city of Vienna, and we see that on a tons per capita and year basis, each Viennese person consumes between 15 and 18 tons of solid materials per year, and we produce a much smaller amount of waste that waste and also products that are exported, and so that the input is larger than the output, which results in a net stock accumulation of 10 to 15 tons per capita and year, and the total stock of Vienna was determined to around 400 tons per capita. So you see, if this would be a stable system, then this stock would double in around 40 or even 30 to 40 years would be the doubling time. So we have a still growing stock there. What we don't really know is how is this stock composed of? So which materials are really behind these 400 tons? Where are these materials? Can they be used? Are these resources for the future? Are they lost forever or what? So there the knowledge is not very well. That the stock is relevant and might be a reservoir for future resource extraction is well known since the 80s already. So Peter Bacini and Paul Brunner from Switzerland, they published these things. But I have to say, really to do research in characterizing this stock was not so much done. It's much easier to do research with respect to flows, because there we have better data and somehow they are visible and you see them, and there you can do research. For example, try to develop technologies to recycle waste streams or so. But this stock here remained a little bit abstract. One of the first good documentations of these stocks has been done by Dominique Wittmer in Switzerland. He determined the stock for Switzerland. You see again, his result was also around 400 tons per capita. Again, his outcome was the stock is dominated by gravel and sand, which is used, for example, for concrete production. The amount of bricks is large or small compared to, let's say, for example, Vienna. We find around 5 to 10 tons of steel per capita, large amounts of plastics, aluminum, and around 300 kilograms of copper and zinc that is contained in this anthropogenic stock. But we also see there are minor materials like cadmium, mercury, or lead, where the amounts are rather small, but they could be problematic if it comes to recycling, because these small amounts here, they can result in a contamination of these rather clean mineral materials, and could be a problem if these minerals should become recycling materials again. So if recycling takes place, you have to make sure that no contamination occurs. Now I would like to convince you that the anthropogenic stock is relevant, and I try to do this by, I selected countries which have significant reserves of, here this example of copper and zinc, but I did not take the absolute numbers of the reserves, but I divided them by the inhabitants in these countries. And in Western Europe country, we think that the stock of copper and zinc is between 200 and 300 kilograms per capita. This is what we would or expect to find, for example, also in Denmark, in the buildings, in the infrastructure, in the long-living goods. And if you compare this number with the per capita reserves of some countries, then we see that these numbers are sometimes already in the same order of magnitude. So with respect to Austria, for example, we would say we don't have any copper and zinc reserves in Austria. We have no primary reserves, but we could say, okay, we have secondary reserves which are significant. And so from our point of view, we think that all the anthropogenic stock is relevant from a resource perspective. Of course, we have to know how much of this stock can be recycled, can be used in future. Is it a reserve or is it a resource? So is it economically extractable, yes or not, for example? And these are still open questions. So if we consider this urban stock, then for us, what we know is that it has increased over the past years. We have seen Vienna, for example, is still growing and growing. We don't know if it's a linear growth or is it a logistic growth. We assume that, for example, for the city of Vienna, the growth will, at some point, it will come to some stagnation. But somehow it's a gray, diffuse area for us. We don't really know how this stock is composed of. And mainly we have two situations. First, if this is now, then we have the buildings that are constructed in the future. And there we have some chance, I would say, to know how these buildings are composed of, which materials are used there. Because the engineers, the architects, if they plan and construct the building, they quite well know which materials are in this building. And one of the keywords is BIM, Building Information Modeling. So this is a modeling of buildings with software, and this software should be able to produce a documentation where you know which materials are contained in your building. But I will not discuss this. I will, in my talk, focus on the already existing building stock, and we designate this as stock research. So we would like to know how are the buildings composed of which already are there. And mainly we can say we have two approaches how to determine the anthropogenic stock. There is the so-called top-down approach and a so-called bottom-up approach. The top-down approach means that you have data from statistical offices, statistical bureaus about, let's say, production data or import data of raw materials. This data is probably quite good. And you have also data about the output of the system, like production of wastes. And the difference between the input, so the imported or the consumption, and the output is the net stock addition, if it's positive, so if the output is smaller than the input. And adding up this net stock addition, if you have such a time series, then you are able to calculate the total amount of the material which is stored in your system, let's say in your city or your national economy. However, we have to say, I said input data is probably quite good, so the data from statistics and so is quite sharp. Outputs are usually not so well documented. So you know, in waste management, often it's not quite clear how the wastes are composed of. Not all wastes are really reported. So again, you have here some uncertainty behind that. The other approach, the so-called bottom-up approach, is that you have single entities like buildings or cars or whatever. You determine the average composition of such an entity, and you sum up all the entities and you get the total amount of your stock. And if it's correctly done and if you have good data, then both results should produce, of course, the same amounts. In reality, we have to say that usually if you do that, the result will not be the same. Probably it seems that quite often the top-down approach seems to overestimate the result, rather, because, as I said, wastes are often not well documented. They somehow lost and in the statistics or wherever, and if they are not there, then you would add them to the stock. And here it's often the case that you don't find all the materials in your entities, let's say in a building or so, yeah? So usually this result is an underestimate, and probably this is rather an overestimate. This is the problem that we have if we want to determine the anthropogenic stocks. I would like to show you now one result for the so-called top-down approach that we have done in Austria for aluminum. So we produced an MFA, a material flow analysis for aluminum, a static MFA for the year 2010. We used a special software to produce this MFA. Software has been produced by us. It's a freeware, everybody can download it. The advantage of the software is that we can consider data uncertainty. All this data that we collect and put into our model has uncertainty. And if you merge much data with uncertainties, you have error propagation in your system. Sometimes your system is overdetermined, so you have more data than you need, but the data are in conflict. Then you can use data reconciliation, and all these things can be done by your software. And the outcome is that you get uncertainties, calculated uncertainties of your flows, and then you know how reliable or how good is my MFA, is my result. In this case, we see Austria, of course, an open system for aluminum. We have much import. We have also some export from semi-products or products. What we can also see is that the input into the use phase here, into the use phase, it doesn't work anymore. So I have now to use the other technology that always works. The input into the use phase is larger than the output, so we have a net stock accumulation of aluminum. What we can also see that not much aluminum remains in the landfills. Most of the aluminum that comes to the waste management system is either recycled or exported for recycling. And what we did now, this is a static system, and we repeated this and we produced a dynamic system. So we had data about, in this area, a data series from the year 1964 onwards, and with certain assumptions about the distribution, for example, of the production data into different use categories, also about the lifetime of the products in the use phase. We can calculate the recycling flow back into the system. Sometimes it was also possible to calibrate the system and sometimes also a little bit to validate the system by independent other data. And this results then in a dynamic model, and the result here would be we can calculate the development of the in-use stock, in this case for aluminum. What we can see is the stock increased considerably since the 60s. Today we have around 3 million tons of aluminum in Austria. Most of the aluminum is in building sector and in the transport sector. And we can also calculate and determine the amount of scrap that has been produced in the past. So today we produce around 120,000 tons of aluminum scrap. Most of the scrap is contained in packaging. Packaging is of course not contained in the stock because this is a short-living product, and we have also much aluminum scrap in the transport sector. But we see also here in the light shaded red area that most of this aluminum is exported via end-of-life vehicles. The total stock today of aluminum in Austria has been determined to 360 kilograms per capita, and the scrap production is around 14 kilograms of aluminum per capita end year. And since we have a dynamic model, we are also able to make predictions for the future. Here this is the example of the total old scrap, and you can see by the year 2050 or so the scrap amount that is produced in Austria is expected to double. Most of the scrap will appear in the transport sector, but also we have increasing scrap outcome of in the building sector and also in the packaging sector. And we think this is important information for the industry because they then have to decide, will they have to build a new smelter, for example, in order to be able to recycle all these growing amounts of aluminum. We have also to say that this is not only a quantitative issue, it's also a qualitative issue, because the quality of this aluminum scrap is important. Is it a cast material or is it wrought material? And also we try to investigate into these topics because, for example, you cannot produce wrought aluminum out of cast aluminum, so recycling is also always a one-way direction, and it could appear that maybe you have too large amounts of cast aluminum which you maybe cannot longer use for recycling. So it's also a qualitative issue, but I cannot go into more details here. I'm coming now to the case study of Vienna, where we try to analyze the building stock in Vienna and its potential for urban mining. And what we did there in the first step is we produced specific material values for different building categories, which means for each building category we tried to produce material intensities, which mean we want to know how much copper, how much aluminum, how much steel, bricks and so on per cubic meter building volume is contained in a typical building of a certain category. In the next step then we analyze the building structure in Vienna, so how old are the buildings, for which purposes are the buildings used. And from this we want to estimate the material output from demolition and deconstruction activities. So the overall goal is to say this is the building stock of Vienna and how much reserves are contained in this building stock. Reserves means that these are economically extractable secondary resources. And for this question we need to produce these material intensities, which I will explain in a minute how we did that. We have to consider the demolition activities in Vienna, and from that we can estimate the demolition quantities and qualities of demolition waste. And finally, we have to combine this with available technologies to say how much of these quantities can be recycled. So what is a reserve and what is a sub-economic resource. How do we now determine the material intensities per building? This is done that my colleagues, they go into buildings which will be deconstructed in a, let's say, in a few days, and a few days before we are allowed to go into these buildings and we take samples from these buildings. Sometimes this is in a destructive or destroying way, so it makes more fun for the people, for my colleagues. So they drill holes into the ceilings or into the floors or walls if they want to find out how is the wall composed of, if it's not clear beforehand. And we also compare our findings with official reports from the waste management companies. We get files, the construction plans from the local authorities for all these buildings, or let's say for even more buildings. And from these construction plans, it's often quite easy to say how much concrete is in such a building, or how much bricks is there, or how much steel for reinforcement is there. We also use data that is available for newer buildings, how they are constructed, and general literature data. Generally, I can say we try to use each information that is somehow available concerning the material composition of buildings. So we collect everything, we take each knowledge that is somehow available. Here you see a few examples of buildings that we have analyzed. This would be a retirement home. On the right upper side you see this is a hospital. This would be a factory, and here this would be a residential building. And all together we have now sampled 15 different buildings. This would be the result for one of these buildings that we have investigated. So we know how many bricks, concrete and so on are in this building. But we also know, for example, with respect to PVC, it's not just that we determine how much PVC is in the building, we also know where is this PVC. So is it in flooring, or is it in cables, or wherever. So we exactly determine in which parts of a building we find certain materials. And this is an intermediate result, and the final result would then be such material intensities that we determine in kilogram material per cubic meter of gross volume of a building. And here you see the result for 8 or so case studies. So I told you up to now we have 15 case studies. And what you can see is the total amount of materials is around between, let's say, 300 and 400 kilograms per cubic meter. And sometimes these material intensities are quite stable. For example, if we go to steel, steel is between 5 and maybe 8 or 9 kilograms per cubic meter, but here you see one building that has a much smaller amount of steel. Why? This is a building which has been erected around 100 or 120 years ago, so there is no steel in the ceilings. It has wooden beams, and this you can see here, for example, because the wood amount in this building is much larger than in a, let's say, in a typical other building. Then we have, for example, copper. Here we have one funny result. For one building, there is more or less no copper in this building. In other buildings, you will find between 0.1 to 0.2 kilograms copper. Here is no copper contained. The reason is this was an industrial building. Usually they have a lot of copper, but this building was open for 2 years. So all the copper has already gone. Before. People went in there and took the copper out, and you can see they were very efficient because my people didn't find anymore some copper there. The question is now, how many such buildings do we have to investigate in order to get reliable material intensities? I cannot really answer this question, but the first estimate you can see here. This would be the number of sample sizes that we have to take from, and this is a result of the samples, of the 15 samples that we already have. And this would be the average uncertainty of the mean value. So if we have taken now 15 samples, you can see that the mean uncertainty of our average value for the copper content is between, let's say, is 15%. For all the other materials here, for gypsum, concrete, plastics and bricks, it's already below 10% uncertainty. So if we continue to take maybe another 10 buildings, then we are already quite, we end up at already quite reasonable uncertainties, I would say. Of course, I'm comparing here a little bit apples and oranges. But the main message here is we don't have to sample 1,000 buildings in Vienna. It's more in the range, let's say, of 30, 40 or 50 buildings. And this is a feasible work. Okay, the next step, so we have our material intensities, more or less, let's say. And the next step is we need to have information about the buildings themselves. When were they constructed, so the construction period, and how are they used? And for these two informations, we have GIS data available in Vienna. Different parts of the municipality have this information, but we receive this information and could merge this information and could combine this. And so what we did is we selected or we analyzed our buildings. We had these case studies. We have also another material information about building composition, and we produced our material intensities, and we have this GIS data on area, height of the building, so we can calculate the volume of each building, and we have this information about utilization and construction period of the buildings. And if we combine these data, then we get an intermediate result. We can differentiate the buildings between residential, commercial, and industrial purpose, and here the construction period, and we can calculate now the average amount of mineral materials in these buildings, organic materials, and metals. And what you can see at first sight is the minerals content increases, so newer buildings seem to have higher metals contents, and the organic content, on the other hand, decreases if it comes to newer building. And this is the structure of the buildings in Vienna. So most of the volume is connects to residential buildings, small amount to commercial and industrial buildings. And what we can also see, large amounts especially for the residential buildings, have been constructed before 1980. So these buildings are rather old. And from these statistics, we can also conclude that in future we will have more deconstruction and demolition materials to expect compared to now. The total stock of Vienna has then calculated to roughly 400 million tons. That's a large number, of course, and it translates into 210 kilograms per capita. This would be also only the weight of the buildings, not of the streets, of the infrastructure, so it's just the buildings, around 210 tons per capita. And this is how these 210 tons are composed of, mostly, of course, of mineral materials. 5 tons are organic materials, and a little bit more than 3 tons would be metals. The mineral part is dominated by concrete and bricks, but you can see compared to the Swiss data that I showed you before, we have a large higher amount of bricks and less amount of concrete. Around 4 tons of wood per capita, we would find there reasonable amounts of, or the considerable amounts of plastics, PVC and here various plastics. And with respect to metals, around 3 tons of steel. Aluminum would be 44 kilograms. Copper and zinc around 30 and 20 kilograms. So the next step that we would like to have is we would try to produce a so-called resource catastrophe. So we are not, of course, not interested in the total amount of Vienna. It's just a nice number, but it doesn't really help. We are interested in single buildings. So we try to be able to calculate the material composition of single buildings and build this up to a so-called resource catastrophe in Vienna. And if we combine these resource catastrophe with, let's say, with predictions or forecasts of deconstruction activities, then we can forecast the quantity and the quality of construction and demolition waste that we will have in future. How can we learn more about deconstruction activities? They are not well reported, we have to say. We get some data from the local authorities, so they give us the address of the building, and if a building is deconstructed, then a notification has to be sent to the authorities, and we should get these notifications. We check this also. We still see that not all buildings are notified if they are deconstructed. Some sites, the buildings are just demolished without notification. We also get some data from wrecking companies, but we don't really know how precise these are. The best thing is what we found out so far is we use so-called orthophotos. These are photos that are taken each year for example, from Vienna. And this is an example of such an orthophoto. Was taken, and 1 year later it looked like this. So, and you have all this GIS data, so you can really calculate this mathematically so that you lose some height there, and you know then there must be some deconstruction activities. Then we can also calculate the amount of materials that have been demolished there, and our goal is, or what we more or less already can, of course with certain uncertainties which have to be reduced. In future we can calculate the materials which have been contained in these buildings, and we can make a calculation about the quantity and quality of the deconstruction demolition waste. In ongoing work that is currently performed, we compare our calculations with official data that is reported to the local authorities. Because meanwhile, these construction demolition wastes, they have to be reported electronically, and but there I cannot really show any results at the moment because we still don't have the data from the local authorities, but this is a step, next step that we want to do. Of course, we are very interested in the things that we determine and the official reports, how they match and if they match and so on. Okay, so let me conclude. I think, and I hope that I could convince you, we think that the anthropogenic stock is relevant from a quantitative and also from a qualitative perspective. And we think also, if we assume that construction demolition waste will increase in future, we have to increase recycling rates for this building stock, also to conserve landfill capacity, because landfill capacity is not endless. So, you know, also I can guess in Denmark, this is a very limited resource, landfill capacity, and we have to conserve as much as possible of this resource. And what we know is, if you want to establish an effective recycling scheme, you have to know the composition of the materials you have to recycle. So we have to know how is this stock composed and which composition we can expect for future construction demolition wastes. We think that we have approaches that can be used to produce such a resource catastrophe, and it's feasible to establish such a resource catastrophe. What needs to be done is now that these approaches have to be routinely applied. I mean, we have developed it now in academic level, but they should be really applied now, because by this application they can be refined and optimized, of course, maybe with scientific advice, but they should be really used now and refined step by step so that they become more and more accurate. And what we still have to do is, of course, we have to classify this urban stock. What is a reserve, so it can be economically extracted and used in future, and what might be a resource and what might be lost forever. Because not all of this anthropogenic stock can be used. I mean, we have to be frank there. And this last step, the classification or the differentiation between reserves and resources, is also part of our ongoing research. One colleague of mine, Andrea Winterstetter, she looked at 3 case studies. A material which is still in use, wind turbines, then materials that have become obsolete, personal computers, and materials that already have become obsolete, old landfills. And she tried to integrate these materials into the UNFC classification scheme, where you have 3 three metrics, like if a project is feasible, for example, technological feasible, if it's economic, and the geological knowledge, so the material knowledge about the material or the reserve or the resource. And she showed that in general, anthropogenic resources can also be characterized by this scheme that has been developed for primary resources. And this would be a way to merge secondary and primary resources, anthropogenic and natural resources, into one scheme of classification. And this would be one step into the direction we would like to see, that we don't differentiate so much between primary resources and secondary resources. For us, this is all the same. These are resources that we have to use in future as good and as efficiently as possible. Thank you very much.